Hello, everyone. In today's lecture, we are going to talk about cohesive energies. So in previous lecture, we talked about the interatomic potentials, and there also we use this term cohesive energies. So basically that was the binding energy. You know, if you remember that LJ curve or Lennard-Jones potential curve, you know that there was a dip. And if you just measure the depth of that well, then you will be given the cohesive energy or the binding energy for that two atoms or molecules in that system. But then we are going to now a little bit extend this cohesive energy term into a more broader system. So previously we talked about two atoms or two molecules when they bind to each other, but now we are going to talk about a whole system, right? So let's get back to the lecture. So here, sorry, you won't be able to see it. Let me get rid of this. Okay, so in here, we are going to talk about the binding energy, cohesive energy, and the enthalpy of sublimation. So this enthalpy of sublimation means now you take a solid, and then you take 1 mole of solid, and then you provide some heat so that this solid, 1 mole of solid, will be evaporated. If you talk about in terms of the pressure and the temperature, it's a combination of pressure and temperature. And usually it is the standard temperature and pressure. Under standard temperature and pressure, you provide some heat, and 1 mole of that solid is now evaporated into a gaseous state, and that is the heat of sublimation or enthalpy of sublimation. And usually this enthalpy of sublimation is equivalent to the binding energy or the cohesive energy for that solid, or it is the binding energy or the cohesive energy which holds that material together, right? So this binding energy, for in a specific case, like in the enthalpy of sublimation, this EB or this EB here, or the binding energy for that system, is equivalent to enthalpy of sublimation, but not in every time, right? Only when the sublimation is happening, we can just assume that this EB is equivalent to that enthalpy of sublimation. But in general, binding energy or cohesive energy is the energy that holds together this material as a solid. So to define it, to give it as an expression, we are using this in terms of epsilon B. If you remember, that is the depth. I mean, if you measure that well depth in the Lennard-Jones potential, here it is the epsilon B. And there's a constant half, and there's Z and Na. Z here is the coordination number. So if you take a unit cell, then you can calculate the coordination number. You take a corner atom, and you're going to calculate how many atoms are in touch with this corner atom or the atom you're interested in, right? For the FCC, we take it as 12. So that means if you take an FCC structure or face-centered cubic structure, and then you take a corner atom, and you're going to find out how many atoms are touching this atom, this corner atom, and that is touching exactly 12 atoms. So that's why we have 12 for FCC. So if you want to learn more about, I'm pretty sure that you have learned about this in your 200 level. But if you want to learn more about it, I have included a YouTube video channel, a YouTube video. Go there and see. It is explaining simple cubic, FCC, BCC, how the coordination number is calculated for those unit cells. And you can even extend it to hexagonal close pack. Right, so so in this equation, so here Z is the coordination number, which you can find out, and Na here is standard notation for the Avogadro number, and epsilon B is the binding energy between two atoms. So if you take a solid that consists of many atoms, right? So the two nearest, I mean, if you take two atoms, like they are the nearest neighbors, and the one between that is given by this epsilon B. And the factor half is to ensure that no bonds are counted twice. Now, if you take two atoms here, there will be another atom there. So if you calculate this, right, the bonds are shared, like this has a bond to this side, this side, this side, this side, top and the bottom. So when you try to calculate the number of bonds, there's a high chance that you're going to count the bonds twice. So to ensure that no bonds are counted twice, we multiply this by half, right? And then binding energy is also referred as the cohesive energy, the heat of vaporization at 0 Kelvin, dissociation energy or energy of formation, right? So what about the lattice energy? Yes, a good point for you to think, right? Oh, sorry. So I wanted to just to, remind you about this, Lennard-Jones potential. If you remember, this is the Lennard-Jones potential equation. And here you have that epsilon, right? That epsilon, there's going to be a B when the, the potential energy is at its lowest value. And if you measure that potential energy, then it's going to be that value. So that is actually given in here, right? So here again, the interatomic potential energy and the enthalpy of sublimation. So we talked about the Lennard-Jones potential in the previous lecture. The binding energy or the cohesive energy between a pair of atoms can be estimated from the enthalpies. It can be enthalpy of sublimation, enthalpy of vaporization, or enthalpy of fusion, which is going to be, when it is melting, solid is melting to a liquid. So that's another way of calculating that binding energy between pair of atoms, or if you know the Lennard-Jones potential, if you model it, you can then again calculate the epsilon B, but that's not the only way, right? So heat of sublimation, as I said, it is roughly equivalent to the, that means you take one mole of solid and you vaporize it to a gaseous space, and that in that case, the binding energy for that solid is going to be roughly equivalent to the heat this heat of sublimation. So based on the energy, so that's why we always go with this energy of sublimation, because it's roughly equivalent to this EB. But if you're using the other ones, the heat enthalpy of vaporization or enthalpy of fusion, then you will have to fiddle a little bit with the coordination number, right? So based on the energy of sublimation, or the energy required to take a solid from the solid state to gaseous state at 0 Kelvin and low pressure, we can rearrange this equation. Now here, instead, and in the previous slide, if you remember, in the previous slide, we take this equation, and here instead of EB, we are substituting it with the enthalpy of sublimation, right? And then we rearrange it so that we get EB, epsilon B in one side, and then we get the expression in terms of enthalpy of sublimation over the coordination number and the Avogadro number. Right. So this is the, I will separately include this, how to find the coordination number. This is just a helping, a slide to help you to get a clear idea about this coordination number. If you are confused, you can go to this YouTube video, you can refer it, or there are better YouTube videos in internet. Just make sure that you're looking at a very reliable one, right? So we talked about that interatomic potential, and then we talked about the enthalpy of sublimation, binding energy, cohesive energy, and all. And where are we heading to, right? So then we are going to come up with, I mean, a way to find the surface energy, right? We are still at the surface, right? So we need to find a way or a model to find out the surface energy. So this is a very, very simple, very basic one, nearest neighbor broken bond model. So in this one, we model it, we consider hard sphere model, right? And the accuracy is 10 to 20% from the true value, which is okay for us as beginners, right? And then if you remember with the Lennard-Jones potential, right? Get this away here. So if you remember, there's a dependency of repulsion term, r to the power 12, negative 12, and then strong, and then short range attractive potential, which has a dependency of r to the power negative 6, right? And this model always utilize low index crystal planes, right? I mean, you will get to know what low index crystal planes means, right? And then assume crystal structure of surface is an extension of the bulk. Density of density of atoms in the face-centered cubic planes decreases as the Miller indices increase. Then surface energy is higher due to dangling bond, like the surface atoms, they are more exposed. Now in the atoms inside the bulk material, they are more covered. Their bonds are like, they have their, I mean, if you take an atom inside, they have nearest neighbors, like they are happily sitting inside, well covered. But on the surface, as I said earlier, they have nearest neighbors towards the inside of the bulk. But what happens to the surface? They don't have that many. I mean, they don't have nearest neighbors to share the bond. So there's like a dangling bond here and there, which are not shared with another atom. So these dangling bonds is the excess energy in the surface. And bond enthalpies are assumed to be independent of temperature. So the assumptions we have in the nearest neighbor broken bond model, first one, each atom is bonded or coordinated to Z nearest neighbor, Z number of nearest neighbors, and only the nearest neighbor energies are considered. Now, if you remember in the Lennard-Jones potential, when the Lennard-Jones potential reaches its minimum, that is the lowest value, then if you calculate that distance, the distance between the two atoms, which is now happily sitting there without any excess net force acting on it, at that point, the atomic distance, we said it's the RE, that is the equilibrium, distance between the two atoms. So if you just push the nearest neighbor another RE away, so the bond between, the strength between these two atoms, will be dropped by, the potential will be dropped by 32 times. So what did we assume there is when it is away from the, like, twice the equilibrium distance, then that exerts a very less force or very less potential on this atom. So that's because of that, in this NNBB model, we only consider the nearest neighbors. So only the nearest neighbor will have the considerable amount of potential or considerable amount of force acting on the other atom, not the next nearest one, right? Only the nearest one. So each bond has an energy epsilon B that is not a function of temperature. It is actually a function of temperature, right? But in this NBB model, we just assume that it's not going to be a function of temperature. The energy is equal to the heat of sublimation per mole divided by the total number of bonds. So I think we discussed this in the previous slide. And the enthalpies and the internal energies are equal. So as I said earlier, the heat of sublimation, we roughly take it as the cohesive energy of that solid. So like this, here the enthalpies and internal energies are going to be equal. Right, as an example, we have what is the expression for surface energy, ES, right? It's given, there are given some units. And then the 111 phase of an phase-centered cubic crystal using the nearest neighbor broken bond model. So if you recall that in 111 plane, there is a central atom surrounded by 6 atoms. So if you take the FCC, right? FCC 111 plane means, I think I have it here, right? So here we have, atoms in corners and as well as in the face. So if you want to get the 111 plane, that means you have to cut that unit cell diagonally. So the central atom is surrounded by 6 atoms. So you have 3 above and 3 below. So there will be for the FCC, if you calculate the coordination number is going to be 12. So if you refer to that YouTube video, that lady is clearly showing you how the coordination number is calculated. So here, the coordination number is 12. So in order to cleave that material in 111 plane, you have to get rid of 3 bonds per atom. Right? So every surface atom then has an excess energy of 3 epsilon over B, and you have to make sure you divide it by 2 so that to make sure that you are not repeatedly counting the same one. So you know that epsilon B is equivalent to 2 times sublimation in enthalpy over Z NA. NA is the Avogadro number and Z here is the coordination number. And we assume that when it's the sublimation enthalpy, then the cohesive energy for that solid is roughly equivalent to sublimation energy. So in our scenario, now we have we have to come up with an expression for surface energy, right? For the surface energy ES of FCC, and we cleave it in 111 plane, and in that case, we know that ES FCC is we have epsilon or epsilon B here is, now you take you take 1 atom, and you when you cleave it, then you're breaking 1 atom, right? So likewise, there's 2, then that's why we have epsilon over B over 2, and likewise there are 3 atoms. So we know the energy, and we know this in terms of epsilon B, and we know epsilon B in terms of heat of enthalpy of sublimation, and then we replace the epsilon B with enthalpy of sublimation and Avogadro number and coordination number, and come up with an equation for the excess surface energy for that FCC structure when we cleave it along the 111 plane. Right. Then the next example, what is the surface energy in gamma the surface energy gamma of the 111 phase of the face-centered cubic silver. So you are given the interatomic distance 0.486 nanometer, radius of an atom 0.114 nanometer, and enthalpy of sublimation is 284 kilojoules per mole. So if one knows the planar density of the FCC of silver in 111 plane, then this calculation is really straightforward. So you want to find out the surface energy, and then what you have to do is you first have to find out the surface energy, the surface energy. If you know, I mean, you can find it out in joule per atom, right? Then you find it out in joule per atom, and then you multiply it by planar density, where you can find out how many atoms. Planar density means in a unit surface, how many atoms are going to be there, and you multiply it by atom, how many free surface energy per atom is available, and then you multiply it by this. Then you are going to get the surface energy in joule per meter square. So you know the expression for ES from the previous slide, and you can just submit it here, and we will see from the previous formula and the formula for the area of a triangle. So this is your face-centered cubic structure, and this is the 111 plane, right? So to find the planar density, you will have to first calculate a surface. And then you have to calculate how many atoms are in that surface. So to do that, you first have to find out the area, which is for the triangle, it's going to be half base times the height, right? To find the planar density for that FCC structure in 111 plane. So the magnitude of the face diagonal, so that is the base, is equivalent to, I mean, if this is A, this is a right angle triangle. So you can just use the Pythagoras theorem, A here, then obviously this is going to be A square root 2, right? So that is this. And then you have to find out this height. If you want to find out this height, then you will have to find out first, you know, here this is the A in the back, and then you have to find out what is this side. Now you know this is the square root, A times square root 2 here. So if you half it, that will be A over square root 2, this distance. So this again will create another right angle triangle, and then apply the Pythagoras theorem. Here it's A, here it's A over square root 2, and then find out the length of this height. So you come up with this type of equation. So the height of the triangle is equivalent to A times square root 3 over 2. Then to find out this area of this triangle, what you have to do is, you know the base, you know the height, right? And then you multiply it like that, and you are going to get something like this. So you know now the area of the triangle, and you are after planar density. So to find planar density, you know the area. Now you will have to find out how many atoms are, you know, when you cleave it, how many atoms are including in that triangle, right? So let's see. You have half of this atom. You have half of this atom. You have half of this atom. So we have 3 halves of an atom. I mean, you have half here, you have half here, you have half here, right? So 3 times half atoms are going to be there, 1.5 atoms, and then you can see there's one portion here, one portion here, and another portion here. So you have to calculate all these three, small section and see how many atoms in total are going to be included in that one plane. So let's see. So there's going to be 3 half atoms and 3 1/6 of an atom. So there's it now total number of atoms included in that 1 plane. And you know the total area of that 1 plane. And then if you know A, I think A is given in the first question here. A is given is 0.486 nanometers. That is for the, atomic distance between 2 atoms. It's given for that unit cell. So you can calculate how many atoms per square meter. That is the planar density for that FCC for the silver. And then if you want to find out the surface energy for that FCC 111 plane for silver, all you have to do is you find out the PD value, the planar density value here, and you know the excess surface energy in terms of atoms per joule. And then all you have to do is just multiply them together and you can find out the surface energy in terms of joules per meter. I hope I am clear enough. If not, we will discuss these examples in a discussion class when we have the physical lectures, probably from next week onward. Right. So this is another example. So you can do the same for 100 and 110 plane. So 100, I hope you remember the solid state lecture. This is a solid state thing like these unit cells and all. So here this 100 means here this is 1, right? But then again, this is parallel to the z-axis and parallel to the y-axis, but it's only intersecting the x-plane. So that's why we have 100. Here 110 means it is intersecting 1 at x, it is intersecting 1 at y, but it is parallel to the z-axis. So that's the plane 110. Right. So you have to do the same for these two planes. So let's take the first one. This is face-centered cubic. So this is the, the cross-sectional plane we are seeing here. So we have 4 corner atoms and a middle atom for that face. That is the 100 plane. So if you cut this, you can find out how many, it's very easy to find the planar density here because the planar density, first you have to find the area, and this is the unit length is A for the unit cell, and here it's A, this is a square, so all you have to do is just multiply the width with the length, that is A square, and then you have to find out how many atoms are going to be inside that, that plane. So there's going to be 1 full atom, right? And 1/4 of atom here, 1/4 of atom here, 1/4 of atom here, and 1/4 of atom. So there will be 4 1/4 of atoms. So altogether there will be 2 complete atoms in this plane if you cleave it along the 100 plane. And to find the planar density, you have to first find out the number of atoms we are going to cleave, like it's a 100. You find out it's 2, and then you have to divide it by the surface, that area, which is A square, and then you can find out how the planar density for that 100 plane. Now let's take this one. It is, here we have to find out how many atoms here in the FCC1 in 110 plane. So we have half an atom here, half an atom here, and then 1/4 of an atom in corners. So if you try to calculate the total number of atoms, then there will be 2 half atoms, and 4 1/4 of an atom. So altogether there will be 2 atoms in 110 plane for the FCC silver. So the planar density for this one is again going to be 2 over, you just have to find out the area. Area here is here, it's A, and you just have to do the Pythagoras theorem and you will find out that it's the, A times square root 2. So it is A square root 2. It's a rectangle. And then you can find out how many atoms, the planar density for that 110 plane. Right. The number of broken bonds for each. So for 100 phase, it's really easy to find. So there are 4 bonds of nearest neighbors at the plane of cleavage that are broken. So if you take the 100 plane, right? If you cut it from the 100 plane, try to calculate how many bonds are going to be broken. So this is 1, 2, 3, 4 bonds. I mean, if you cleave it from here, these atoms are going to be, now the coordination number you can easily calculate from here. The coordination number for the center atom, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So the coordination number is 12. But if you cleave it from that 111 plane, then these 4 atoms are going to be, separated. So for this center atom, there will be 4 dangling bonds, which are not now shared by or, used by another atom. For the 110 plane, it's a bit difficult to visualize, right? So there will be 5 bonds that are broken, and according to some, there are, 6. You just have to, it's a 3D modeling thing. So you can find out if you know the planar density, and then if you know the, you can find it out easily. You can calculate the surface energy for that 1110. Right. So obviously, this gives a lower value for surface energy because fewer broken bonds. Right. So that is, for some says we are breaking, 6 atoms, and some says we are breaking 5 bonds for 110 plane. So if we use it for the 6 BB scenario, we will get 2 joules per meter square. And for 5 broken bond scenario, you're getting 1.66 joule per meter. So if we break less amount of bonds, then the surface, the amount of dangling bonds are lower. So the lower surface energy will be achieved, right? Let me get this out from here. Sorry for that. Right. So surface energy hierarchy. So if we just keep in touch with that surface energy we calculated in earlier for the FCC, we took the silver as for an example, and the surface energies for 110 is higher than 100 and 111. Let's go back and see whether it's true or not, right? So here, this is for 111 plane. We calculated that is around 0.163 joule per square meter, right? That is 0.163. That is for 111 plane. And for 100, we are going to have 100, we are going to have 1.88 joule per square meter, right? That is for 110. 100. And for 110, there are 2 scenarios. One is either 2 or the other is 1.66. Let's see. So here, the lowest value, which was around 1.63, is achieved for 111 plane, right? Then we got 1.88 for 100 plane, and then for 6 broken bond scenario, we got 2 joules, that is for 110 plane. So the lowest surface energy is achieved for 111 plane. The second lowest energy, surface energy is achieved for 100, and the third surface free energy is achieved for 110. So that means this has the highest surface energy. This is the second highest, the second higher, the bit lower, but this is the lowest. So the lowest surface energy means it's more stable, right? Right. So this is, they have averaged the, the 2 plane, the 3, taking 3 planes into account. They have just averaged it. The average surface energy for silver is around 1.2 plus or minus 0.06 joule per square meter. For, in our case, it would be either 1.35 or 1.25. That's why we said that there's a 10 to 20% deviation from the correct, correct value. But this nearest neighbor broken bond model is a good model as a start, right? So if just keep this in mind, the higher index planes like 111, they have a lower surface energy. Therefore, they are more stable compared to other surfaces. Right. So I'm going to skip this part. So here just surface energy calculated for silver using different methods. So nearest neighbor broken bond model with these 6 broken bonds for 111 plane, we achieve 1.35. And if we assume for 111 plane, there were 5 bonds broken, then it's 1.25, and there were other. And the actual experimental value lies around like 1.25. So, not too bad. So the work function is another way of, we talk about this, minimum energy to remove an electron from the surface at its Fermi level. But these are not surface atoms. These are like innermost electrons, right? So this photoelectric function is pi photoelectric is given as H epsilon H mu naught. And thermionic work function for like hot cathodes, there's this KB, this, Planck constant and all coming into play. So J here is the current density, and A here is the Richardson's constant, and which is given by another, shenanigan, which I'm not going to go into detail here. But, just keep this in mind. The work function of a material just give you an idea about the minimum energy required to remove an electron from the surface. And if you try to calculate the relative surface stability, then the work function for 111 plane in a face-centered cubic is higher compared to work function of a face-centered cubic 100 plane, and work function of an FCC 110 plane. So this reflects the surface stability. So in previous slide, we discussed that how the surface energy is minimum for FCC 111 plane and little bit higher for 100 and highest for 110. So 110 plane has the highest surface energy, therefore it's very unstable. And 111 plane is has the lowest surface energy, therefore it is highly stable. So that also reflects from this relative surface stability when we talk in terms of the work function, right? Because the work function for 111 plane in the face-centered cubic is highest. So the higher the work function, lower the surface energy, and higher the surface stability. So surface energy reflects the surface stability. The plane with the lowest surface energy, that is the 111 family, will have the highest electron work function because it is more stable and it will take most energy to pluck an electron from that surface. So if you, here I have given some, example of surface energies. Here for silver, you can see 111 plane has the highest work function compared to 100 or 110. Right? For every silver, copper, nickel, you can see 111 plane has the highest electronic work function. So that means the 111 plane is more stable. So this will be used in selective etching. Selective etching means, let's take nickel oxide crystal and we are going to etch it. First, we take the cubic nickel oxide crystal, and when we etch it, what happens? 100 plane is not that stable. It's not the most stable one. The most stable one is the 111 plane. So what happens? It will be, gradually etched. When you put it in a certain chemical, that will be etched, and then finally it will come to its most stable form, which is a octahedral morphology with all 111 plane. So you can see all they have these triangular 111 plane. So because when we perform that selective etching, it is because it's of the first configuration was not that stable, it has more excess surface energy, it removes it and comes to a very stable morphology. So the least stable planar faces get etched away to leave the most stable faces. So this is another example, like we use this selective etching in nanotechnology to synthesize nanoparticles. Right, so another example is the least stable planar faces get etched away. That means the planes with high surface energies etched away, leaving the most stable faces. So for anisotropic etching proceeds for silicon. I'm extremely sorry for silicon. Here, this is silicon iodide. Anisotropic etching, we do it with KOH. And then what happens? We have SiO4 to the power, and we have K plus, and hydrogen gas is coming out. The etching rate for low index planar surface for silicon, right? For 110, it's 1.5 micrometer per minimum. So per minute. So per minute, 1.5 micrometer, that much of area, or that much of length is etched away for 110. And for 111 plane, that etching is really, really low. You can see per minute that will only get rid of 0.005 depth. So while this 1110 plane is slowly etching, all the other planes will be very quickly etched away. So that will be, we are left with highly stable 111 plane silicon structure. So with isotropic etching, trenches look like inverted C with an isotropic etching. So I'm not going to go into detail about this isotropic etching and anisotropic etching, because we are going to talk about them in detail when we talk about the fabrication techniques. So for now, I'm going to skip this. And the work function of a material increases in general with decreasing particle size, right? So that also you can imagine. So this is a particle size in nanometers. You can see the work function is getting increasing. That means when the particle size is lower, it will be really, really hard to get or to separate electron from that nanoparticle. Right. So with this, I'm going to conclude my lecture on cohesive energy. Thank you all. I'll meet you with the next lecture.